So I'm going to be explaining getList, which is a method that I wrote in map.java for my Bloons Tower Defense final project. So this is the function, and so essentially why we wrote this function is in the map1.java class, we store endpoints in the track, which is what the balloon walks on. So endpoints are like, for example, this is a segment. A segment would be a continuous path that the balloon would walk on, and then after this endpoint, like the path, the direction would change to up. So here we can see the y coordinate. Y coordinate is constant, but here the x coordinate is constant, so it goes up. So here it goes right, then it goes up, and so on. So we only store the endpoints, which is a pretty lazy and clever approach. So the way we implement this is, of course, for rendering the path, we want every coordinate, not just the endpoints. And so to render it, we need a list of all the coordinates. And so this getList function actually creates all the coordinates for us. So every coordinate is stored as a float array, where the 0th index represents the x coordinate and the first index represents the y coordinate. And this is returned as an array list of float arrays, which is points. So we initialize that, then we go through the track, which again is the endpoints. And for each point, we will store we will store 0, x1 and x1 y1 and x2 y2. So this is the start point of this segment, and this is the end point of this segment. So then we store the absolute difference between the x coordinates of the start point and end point, and then the absolute difference between the y coordinates of the start point and end point. So how much will it move by x? How much will it move by y? Of course, like we saw, for our purpose, we will only one of dx and dy will be 0, but it's not won't be the case if we have like slanted, like diagonal path segments, which we don't have for now. We only have vertical or horizontal ones. But with this function was designed keeping in mind that we may expand it to include diagonal path segments as well. So this algorithm is called the Digital Differential Analyzer algorithm, or DDA algorithm. So after this, we store the number of steps, which in this case works out to be the maximum of this difference of the x and how much difference of y. So the steps is the maximum of how much we move in the x direction and how much we move in the y direction. It's the maximum. Which one is bigger? This is an error checker, which is just there to make sure that x1, y1, and x2, y2 are not the same coordinate, meaning the start point and end point of the segment are not the same, meaning the segment length would be 0. In that case, I would do nothing, but we wanted to do something, so this steps, it makes it one step. So, of course, in our case, that's not necessary because we hard-coded the track and start points and endpoints, and so we know that there will be no duplicate start point endpoint. We know that the tracks will at least have non-zero length. We can say that. We know that each segment will have a non-zero length. So after we've done this, we get the increment for the x direction and the increment for the y direction, which is the difference between the x2 and x1 or y2 and y1 over the step. It just tells us how much we need to move per step for each step. And then we just have, these are like pointer variables, which is what I like to call them. And it just refers to float x is initially x1 and float y is initially y1. And eventually we want to get to x2, y2. So it starts at x1, y1, and it ends at x2, y2. Then we just go through all the steps and we say for each step, if it's the first step, meaning there are no points added to the points array list yet, in that case, we just add it into the points array list. We add xy to the points array list. We round it first, though, because it's a float, and we want to store it. We want to render integer coordinates, because each pixel is not a float; it's an integer. So, and after that, if there's already a pointer there, meaning this is the second or after step, so like it's after the first step. The first step has already been made, and we had a check here. This check makes sure that the point we're trying to push in right now hasn't already been pushed in previously. That just ensures that it just checks, is current xy equal to most recent xy that was pushed last time. So 0 represents, of course, x, and 1 in this case represents y. So this is just an error check for that. It's not an error check, sorry. It's just a check for that, because we don't want to push in the same point twice. And that occurs if you round it, like let's say the increment is 0.1 and the previous coordinate was 1.1, 2.1, and then the next coordinate will become 1.2, 2.2. They'll both round to 1, 2, 1, 2. So we just be pushing in 1, 2, 1, 2 twice, which is not relevant for us. We don't want to render the same point twice. So we just, if it's the same, we don't render it. If it's different though, if after rounding it we got a different point, we push that into the points array list. And then as we discussed earlier, we just increment x and y for each step by whatever the increment is per step. And then we just continue on and on until all steps are done and we've reached x2, y2. And then we just return the points array list, and we're done. That has all the points for the whole track so that it can be rendered on the screen. So yeah, this is just the digital differential analyzer algorithm. It's important to note that this can be extended. Our maps can be extended because of this algorithm to include like slanted or diagonal segments as well. Right now we only have horizontal and vertical ones for simplicity, but if we chose to expand it, our getlist method would actually support that, which is nice. So this is map1.java in Bloons Tower Defense 6, so the final project that we made. So there's abstraction in map1.java, which can be seen right here. And so the user of map1 doesn't need to know how like the map class works internally, and everything needed is handled behind the scenes, like by the by the superclass called map.java. So abstraction involves hiding the implementation details and showing the user only the necessary parts. So that's abstraction. There's also encapsulation in map1.java, and that can be seen right here in this segment of the code. So these fields are stored as a private static final float. So they're private static final variables, which means that they're not accessible by other classes outside of map1.java. And that means that their values can't be changed by other parts of the program. So this like protects like their integrity and ensures that the map1 the map1.java remains consistent. And it's also important to note that private represents that it's an access modifier, which means that only this class can access this variable, and it hides like the internal details from other classes. And then there's static. Static means that it belongs to the class and not to instances of this class. So, and this is shared across all objects of the class, and you can access it without creating an object. And there's final. And final here, it just means that this variable's value cannot be changed once it's been assigned, and it makes the variable a constant. And then we can also see some inheritance here, right here. And map1.java inherits from the map class, which means that it gets all the properties defined in map, such as like drawing the map from using the endpoints, the track, and other behavior defined in the map. And that allows map1 to reuse and extend the functionality of the map instead of recreating everything that map already has. So it allows you to use the map class, but add some more like customization or make a new file that already has all of the methods and functionality defined within the map class.